Hey guys, today we're going to learn about differentiation. We want to understand it. In this video, I'm going to talk about understanding the gradient formula, graphical understanding of finding the gradient at one point, and deriving the gradient function of x squared, and so on. Now, understanding the gradient formula. This is just a normal linear graph. This is the gradient formula for the linear graph. I want to focus on that specific point. I'm going to enlarge it. We know that that difference in height is just a difference in y. And we can use the term dy, which means difference in y, to represent that difference, that length of that triangle. And down here, this is just a difference in x. Between 2 points, that's the difference in x, so I'm going to represent that with a dx. So that means the gradient would be dy against dx, if we were to use the gradient formula to understand this. That is why in this chapter, you'll be seeing a lot of dy dx's. Now, we want to find the derivative, or the gradient function of x squared. For example, I have this graph. Compared to what we did before, that was a linear graph, and this is a quadratic graph because it's x squared. Let's draw a gradient line. I just simply drew a line, but we know that this thing is actually touching 2 points. That means it's not going to be accurate. I want to know the gradient at one specific point and for every single point on this graph. So what I'm going to do is I'm gonna bring those 2 points closer. By the way, this line is called a secant because it's touching 2 points. We want a tangent. Tangent means touching 1 point and 1 point only. So I'm gonna bring it closer and closer and closer until it's only touching at 1 point. Okay, until the 2 points on top of each other. This is what we call a tangent. And this will give us the gradient of that point, which is the 1 point that both the points are on top of each other in. Okay, so basically I just move that secant line slowly until both the points are one on top of each other. So this will give us the tangent. This understanding is important, okay? What I'm doing is I am bringing the 2 points closer. That means the x values are getting closer, as close as possible, until it's almost 0, which is one on top of each other. So now we're going to look at the gradient of 1 point of the quadratic function. I can use the triangle, which I use to illustrate the gradient of the linear function. I want to focus on this triangle. I'm going to enlarge it. So, for example, this is some random x. I don't know what this point is, but this is just some random x. If I were to move forward some distance, I'm going to call that d. So, at this point, this is going to be x plus d as the distance. The d is going to be the distance, so x plus d is going to be my new point. Likewise, if I were to look at the height, let's say this is some random height fx. And I want to go on top a little bit. I want to be at the same point as x plus d, so that's going to be fx plus d. So let me just recap. I started from x and I moved a little distance. I called that distance d, so that means my final destination would be x plus d. And I plugged these 2 things into my function, so it gave me the same results. Now, let's just bring out the gradient formula for any linear function, because we have converted that quadratic function into a linear, so to speak. So I'm gonna just substitute the x squared with x plus d. As you can see, that's the only thing that's being replaced. And then I'm going to replace the y values, y2 minus y1, with x plus d and fx. I also replace the x1 with the x, which is that part. So if you can't understand this part, pause the video, study what I'm substituting. It's nothing special. I'm just plugging my y2 and y1s, x2 and x1s into the formula. I can see that the denominator I am able to simplify. This is just x minus x, so I'm going to be left with d. This formula is what we call the f prime formula, or the derivative, or the gradient function. But this thing can work differently for different graphs. Now, I could try plugging my d equals 0. D is just the difference between 2 points, and I can see that now they're one on top of each other, that d would be 0. But that wouldn't work because in this case my fraction has a denominator which equals to 0. And this would break. If I try plugging in 3 over 0 in my calculator, or 5 over 0, or even 3000 over 0, you would find that it would give you a math error because over 0 is just not possible for any fraction. I can make a separate video explaining why. So what can I do? I can actually take the limit where d approaches 0, where the difference between those 2 points, which is represented by d, is approaching 0. It's never going to get there, but it's approaching there. What am I going to get? That's what I want to find out in this case. So for this graph, it's an x squared graph. It's a quadratic graph. So I'm going to plug in my x squared coordinates into these spaces. So what is it going to look like? I know that's not going to work. Okay, what is it going to look like? It's going to be this limit, and now I'm going to substitute my x squared so that fx plus d, that function, is going to be x plus d squared. That fx is going to just be x squared. That d does not change because it has no x value and is not a function. From here, I can actually expand this part. So now I have x squared plus 2dx plus d squared minus x squared. These two x's can cancel each other. So now I'm left with 2dx plus d squared over d. I can actually cancel the d's too. I can cross out the d's, so it's going to give me 2x plus d. And just a reminder, you need to write this limit for every line that you do. Okay, because it's an understanding of where d is approaching 0 and not actually equaling to 0. And we need to state this because this is very important for every line until we do something with it. So now I've simplified down to its core. It's 2x plus d. If I plug my d equals 0 into that d spot, it should be fine now. It's just going to be my 2x plus 0, and that's just going to be 2x. So you find that when we take the gradient function of an x squared graph, we get 2x. That means whichever point on that graph, whenever I find its gradient, it's going to be 2 of x of that specific point. That's going to be the gradient. And we're going to do a few exercises on that later on. So if I want to find the gradient function of an x cubed graph, so I find that when I differentiate x cubed, I get 3x squared. That's all the information we need. We can actually generate a pattern from this. So establishing a pattern, from fx equals x squared, when we differentiate we get 2x. From x cubed, why do we take x cubed? Because it's a constant function. Okay, we're forming a pattern, so I'm taking x squared, x cubed, x powered 4, all these things, so everything's in order. So we can actually compare the derivative because they should be in order as well. Now let's notice something. I want to focus on this line. X squared, I see that the 2 has gone to the front and that x has stayed. Okay, interesting. X cubed, the 3 has also gone to the front, but this time x has a 2 at the back. Okay, so the first thing I must know is the powers will always go to the front. That's something I notice. The second thing I notice is the power on the x for the first line isn't actually gone, it's actually powered 1. So after I differentiate, the x squared has become an x powered 1. For this second line, the x cubed has become an x squared. So you can see, after I put the power, after I bring the power to the front, I have to take that power and have to minus 1 to it. So can we guess what the derivative of x powered 4 is? It's going to be simple. I'm going to bring the 4 to the front, so it's going to be 4x, and the power is going to minus 1. So it's going to be 4x cubed. That's all. So the formula would just be this. If I have x powered something, if I differentiate, that something is going to move to the front, and that something is also going to minus 1 at the same time. This is the formula that all of you will have to know. For example, if I have this function, find fx. which is f prime x. Sorry, find f prime x, which is just the derivative or the gradient function, whatever you want to call it. Right, so again, I'm going to differentiate these. That is just going to be, I'm going to bring the 2 to the front. That's going to be 2x, 2 minus 1. And that 2x is just going to be 2. Because the x is going to be gone. The x is going to be, that power 1, that x power 1 from that 2x is going to move to the front. And then that 1 is going to minus 1. So I can simplify this line, and it gives me 2x plus 2. That's it. So that means this gradient function, if I want to find out the gradient at any point on this graph, in this graph, fx equals x squared plus 2x, I'll be able to use this gradient function to find out the gradient on every spot I want to know. Given fx equals to this, again, I'm going to find f prime x, which is the derivative. I'm going to bring that 2 to the front, so it's going to be here. Okay, and then that 2 at the power side is going to minus 1, but that 4 doesn't change. Right, that 4 doesn't change. Actually, that 4 is going to be gone. This is just a rule that you need to know. I can also prove that the normal numbers, anything without an x, is going to disappear, but I'm not going to do it in this video. I might do it in a separate video. Just remember, if you have a normal number, just remove that completely. So I'm going to focus on this part. Okay, and it's going to be 4x minus 0. Okay, that thing's going to disappear, and then that's going to equal 4x. Okay, you can actually skip the minus 0. It's not important in this line. Now, given this function, okay, y equals to this. So if you want to differentiate y, it's going to be dy dx. They mean the same thing. I can call it, if the function is in fx, that means if I differentiate, it's going to be f prime x. If the function is y, I can either call it an y prime or dy dx. But in this case, I'm going to use dy dx. So again, from that 3x powered 4, that 4 is going to go to the front, it's in red, and that 4 is going to minus 1. For 9x squared, the 2 is going to move to the front here, and then the 2 is going to minus 1. For 2x, that 1 is going to move to the front. Oh, I forgot. Okay, I must have missed it. And that 1 is going to minus 1, and that 3 is going to disappear, like I said. So I can simplify this line. 4 times 3 is 12, x cubed. 9 times 2 is 18, x. And then this is actually a plus 2. There's a typo. Can I cancel this? Yeah. Okay, so this x is just gone, okay? That because that 1 minus 1, this part should give me 0. So it should not have a power of anything. So, anyways, thanks for watching. Remember to like, share, and subscribe.